Sorry for the intermission. Now we are looking at this. What we have, like we said, the energy momentum tensor in the form we've obtained is not unique, and worse for us in this case is not even symmetric. So we are going to add this term to it, like we said, given the fact that in the form in which we have it here, minus 1 over 4 pi a mu multiplied by this, comma k. This is antisymmetric in mu and k. And adding this term to this, of course, still gives us some conserved quantity, so which again confirms what we've been saying, that this is not unique. Now, if we had to combine this with this, again, I can write this term in the next step as simply minus 1 over 4 pi a mu comma k or kappa, and this is that. I can do that like we stated already. We said that the charges are absent, so in this case, f mu kappa comma kappa is simply equal to 0. So by Leibniz rule, we simply have just this term as a non-zero term. So in the next step, you can see, if I combine these two terms, I have 1 over 4 pi common to both. I'm going to have here kappa mu minus a mu comma kappa, multiply both of them. You can see what is common to both of them. So again, for the sake of convenience and getting what would be most suitable for us, we have carefully selected this or constructed this to be able to make this happen. Of course, what is here in the bracket, as you can see, will be f mu kappa, following the notation again that we talked about right from the beginning. So following this all along, we are getting into, we finally obtain that this is the same thing as some 1 over 4 pi f mu kappa f nu kappa plus the chronicle delta nu L. That is what you get. But then again, what originally was a Lagrangian? A Lagrangian was the Maxwell Lagrangian, or the Lagrangian of classical electrodynamics, which we have already written in the beginning. So, and this Lagrangian L is equal to minus 1 over 16 pi f alpha beta f alpha beta. That was what we started with. So that's our Lagrangian. So at this point in time, we can simply write this whole expression as 1 over 4 pi, opening a bracket, mu k, mu kappa, minus, minus because of that. And then again, I'm going to have 1 over 4, because then the 4 will multiply this to give me 16. And then here is going to be, so I have a chronicle delta mu nu. This will be f alpha beta. So, and this is T here nu mu. This now is our energy momentum tensor. Still conserved, as we have noted right from the beginning, but this time around is symmetric. Symmetric in nu and mu. Of course, you can see in this second term, it will be inconsequential, like we stated right from the beginning. It wouldn't matter on the chronicle delta. But then if I had either placed nu here and mu here, in the end, it's still going to give me the same results. There will be no changes. Remember, because I have some kappa following me around. And then if I had placed mu or nu here, there's no way of knowing. By the way, because I could have at the same time raised both these covariant indices to become contravariant and lower this to become contravariant. So when I do that manipulation, at the end of the day, you realize that this is the same. Of course, to fulfill all righteousness, probably it will have been nice. By the way, so I should make this notation. I should say this. Lambda and Lipschitz defined their energy momentum to be given by this expression. They defined that out of the blue, actually. I didn't say the derivation in that remarkable book, but with this definition, you can see what we had originally was the chronicle delta multiplying our Lagrangian. This is what they used to denote their Lagrangian minus this one. But instead, this time around, is a change in sign. And so they obtained this expression. As you can see, this is what they obtained. And of course, in order to be in line or to follow what they've gotten, we will simply just have to raise mu everywhere. And if we raised mu everywhere, we are still going to get the same expression they got again, except for the sign difference. like we said before. This in their own case is plus and minus here. So if I raise this mu, it could become rho, and in the end, so something like this, T, let me say, because what it will mean is for me to use some G rho, I guess, G rho, no, that will be down here, G rho mu, and then I'm going to have rho here, and then nu, that will then give me 1 over 4 pi. I'm going to have again G rho mu here, and this is going to give me F. Of course, what I'm going to have again is rho, and then kappa, F nu kappa, minus 1 over 4. Again, the G rho mu follows me all along, everywhere, so I'll be raising it. Again, even though this is just a chronicle delta, so let me just have that multiplying through. So one thing you can say, this becomes rho nu F alpha beta F alpha beta. Okay, a word on this, because this is a chronicle delta. Like we said, if it's a chronicle delta, although it's going to be special here, let's come to that right now in a moment. Now, Lambda and Lifshitz notes that their energy momentum tensor is traceless, in the sense that, of course, when you lower kappa here, in this case, you will simply obtain our expression. And if you obtain our expression, contracting nu and mu, you will obtain this to be equal to 0. How do you get that to be equal to 0? If you contracted nu and mu, you will simply obtain nu and mu here to be the same. And it will be just like having some alpha alpha, and kappa kappa also, I might as well change to beta beta. But then again, contracting it on this term here, or factor nu mu, later on in our development in this lecture, especially when we talk about the linearized theory of gravitational waves, we are going to come across this object, the Minkowski metric, which again is specialized and which is what is appropriate for the energy momentum tensor, as long as the four momentum or four vector notation formalism is consigned when we're talking about classical electrodynamics. It's purely spatial relativistic, and in that case, using this to denote the Minkowski metric, we show that this, by the way, is simply the same thing as chronicle delta. We are going to see this expression later on in these lectures. But the point here is to say that when we have this attached to an expression like this, you can see it's not like I can say, okay, change mu to nu or nu to mu anywhere here. But if I have mu like this, for this, what you call a chronicle delta is just the same here on the Minkowski metric. And for the four-dimensional space, this will be equal to 4. And being equal to 4, of course, in this case, it will cancel this 4. And then again, having this to be F alpha beta, just like I've contracted this and this, so it might as well be some F alpha beta or F alpha kappa, which will be the same as the second term. This subtracting that will give 0 eventually. We are going to solve this problem again in a different lecture, so I wouldn't want to dwell much on that. But it just goes to tell you the different notations, some other kind of definition of the energy momentum tensor that you are most likely to meet. And this is coming from the classical theory of fields of Landau and Lifshitz. Okay. With this denotation, so as we're saying, you might as well know, of course, in the end, I can just drop this G sub rho mu, and if I like, call these rows all along mu all over again. So that in the end, sorry for that, so that in the end, this might as well be this, equal to 1 over 4 pi, F here, mu kappa, F nu kappa, minus 1 over 4. I have here with me, again, it wouldn't matter, but then, like we've stated right from the beginning, dropping this, I have here just some kind of combination, which I might as well. So I'm going to be careful here to just use the Minkowski metric. So instead of rho nu, it becomes this. And then, of course, this gives me alpha beta, F alpha beta. So this, again, is another expression. And this you can find especially in Rolich, Fritz Rolich textbook on the theory of charged particles. So again, this is just another way of writing this same energy momentum tensor. And these two are completely equivalent or the same. And of course, this is the form again that this is the form you find in Landau and Lifshitz textbook. So you can see that with what we have obtained at this point in time, it wouldn't matter again, like I said, this kappa and kappa I could raise or lower because it wouldn't, with whatever metric tensor I use to raise this, I can use to lower that. And so if I interchange mu and nu, it wouldn't really matter on this expression. And of course, obviously, you can see that that is the same for this one here. Now, one important point we have to take note of is this. When I add such a term as this, like we've just done, by the way, in Landau and Lifshitz, if you are performing this calculation, along the line you come here, you're going to get a minus. So when you add such antisymmetric term to this non-unique energy momentum tensor, you will have here a plus instead of a minus. Well, that is just by the way. So moving on very quickly to point out something here, which has to do with the definition of the energy, the form momentum, sorry, not energy momentum. The form momentum here in this case, for instance, P beta equal to 1 over C integral of this energy momentum tensor ds sub gamma. Now the concern here is, for instance, we said that the energy momentum tensor, especially in the way we have defined it and used it so far, is not unique. So does that mean also that the form momentum is not unique? So for instance, can I define another form momentum like this, say 1 over C integral of T prime beta gamma ds sub gamma, whereby if I said, for instance, that T beta gamma is equal to this is prime, so that T beta gamma plus, I'm going to try to use some term here, this is some theta beta gamma kappa dx kappa. This expression, by the way, I am assuming to be antisymmetric in gamma and kappa. So this will be minus of theta beta kappa gamma. That will be minus that. So if that is the case, the question here is, of course, like we stated before, because looking at this spatially, if I were to differentiate this whole expression with respect to x gamma, I'll get something like this, comma gamma, and then here I'm going to have plus. This will be the 2 here, beta gamma kappa dx kappa dx gamma. Right from the beginning and from our definition and everything, this first term is 0. But the second term again is 0, like we have shown at least twice in this same lecture. Yeah, it's 0 because it's antisymmetric in these last 2 indices. And in these last two indices again, with respect to both x kappa and x, or x kappa and x gamma, is with respect to those two that I'm differentiating the objects. You can see differentiating that twice. So we have shown that this such an object defined as that is also equal to 0. Now the idea is, if you have defined an energy momentum tensor to be this, and then you just added some term which you believe will still give us something conservative, or in other words, which we still need to say T prime beta gamma comma gamma to be equal to 0. What then becomes of the form momentum? Is the form momentum still going to be the same? Is the form momentum also not unique? So to proceed or to find out, you're going to have to substitute this expression which we have for this. So we are still going to have what we expect to be the normal thing plus. Here I'm going to have 1 over C, an integral, but it's going to be here d theta. I have here beta gamma kappa, dx kappa, and here dx gamma. So what we have here is the original form momentum, sorry, not prime, the original form momentum before the addition of some objects. Now this second term, if this second term is not 0, then definitely the form momentum also isn't unique. But the form momentum has to be unique. So this has to be 0 one way or the other. And how can we show that that is 0? I think at this point I can simply erase what I've written. We can show that it is 0 by simply considering the fact that 1 over C excuse me, beta kappa gamma, and then here the x kappa, the x here gamma. By what we see here, we have two indices, this kappa kappa, gamma gamma. I can interchange both of them like we've always said. If I have such two indices, like I can have, for instance, let me just use something compact to illustrate my point. We've stated that if we have something like, say, beta gamma kappa and gamma kappa, this is the same thing. Let me put kappa here and gamma here. This is the same thing as me interchanging gamma and kappa. Interchanging these two. And this is the same thing for me to say this is theta beta kappa gamma here, but then here gamma kappa. These two are the same. The same in the sense that I've simply just interchanged two dummy indices. And this has been a trick we have used over and over again. And so if they are the same, I can write this expression as simply interchanging the two, the sum of two the same things. For instance, this will be, I simply have the first term exactly the way it should be, gamma this, and this will be the x kappa, but then I'm going to have the x gamma. And this is going to be plus the theta here, beta, but kappa, gamma, and then the x here becomes gamma, but then the s kappa. So this and this are the same, because all I've done here is to have interchanged, what is this? What is it called? Kappa and gamma. Kappa and gamma. Gamma is a dummy index on this term. Kappa is a dummy index on this term. I can interchange the two, and if I did that, this is what I will obtain. And of course, what I've done here is simply to have added the same thing twice. So it's just like saying A is equal to A plus A. It doesn't make sense. A is simply equal to half A plus A. So that was why I added this half here, because all I've done is simply add the same thing to itself. So I'm dividing it by 2, and of course this is just the same with what I've got here on the left hand side. Now if that is true, of course what I intend to do here is to exploit the antisymmetry of this object. This object I've stated already is antisymmetric in gamma and kappa. So that in the end, this is the same thing as 1 over 2c, the integral of the theta, beta gamma kappa, the x kappa, the s gamma, but minus, this becomes here beta, but then I have here gamma, kappa, the s here becomes still gamma, and then the s kappa. Nothing changed with respect to that. Of course, one thing I can do is to write it in such a way that this is the same thing as 1 over 2c. You can agree with me that this is the same thing as some ds gamma d the s kappa minus the s kappa d the s the x gamma, and then here I have with me theta beta gamma kappa. Yeah, that is just the same with what I have here. So I just brought this at the back of this at the back of that, and then you can see, of course, by our antisymmetric permutation which we performed here, what is here is just the same as what is that. I can pull that out of the bracket, and then what I have here we can call some f, the f gamma kappa, well, whichever order I choose, but I can choose gamma kappa and put some star. This notation is familiar, or I could say quite peculiar to Landau and Lifshitz book. So you can look into that to confirm this. So this is the same thing as, at this point in time, I think I will prefer to put the other one there first. Beta kappa gamma, the f gamma kappa. So in other words, this whole differential operator, linear differential operator here, I've named the f gamma kappa. Now here I'm looking at a statement, and I would like us to just consider this for a moment. And what we have done here is simply to redefine an integral. This integral, you can see what we have finally, or what we've just expressed finally, is just that. And this is what is important to us, this factor here, or that integral. That is what I've called I prime. If I have that I prime defined in that form, I could simply redefine that by, of course, using this expression, going back to express this in terms of the S gamma, the S kappa, or just leaving it in this form, and then going ahead to express what is to be obtained. So you see here, what we are trying to state specifically is we can transform the integral over a two-dimensional surface, which is this, by the way, into an integral over the hypersurface spanning and spanning it. So we are choosing here a hypersurface that is okay. So what we have done up to is quite interesting. We have been able to rewrite this integral in this form into something like this. Of course, quite interesting is you might think of this as some kind of Gauss theorem, whereby the d dx the x kappa disappears, and what we are left with is this. Of course, what we had originally was p prime beta to be equal to this, which is equal to that plus that. Now, what we have, of course, this integration is still performed over the hypersurface. This is a hypersurface, and then plus this. Now, what we are going to do is simply to extend the integration of this here over the ordinary surface that spans this hypersurface. And this hypersurface is located at infinity of a three-dimensional space. And since at infinity we have neither charges nor fields, this integral here has to be equal to 0 because we're integrating over all space. So that in the end, p prime beta is just the same thing as p beta. In other words, even though our energy momentum tensor isn't unique, our form momentum, as a matter of fact, is unique. So even though this isn't unique, this is unique. So at this point we stop. Again, further when we meet next, we shall continue with the exploitation of these properties.